I think we probably should get started. So welcome to the last day of lectures. And so as I described yesterday, we started the class yesterday setting up the entire conservation equations. And very rapidly, you realize that it becomes intractable. No? So it is impossible to actually work the problem. And so we went to the complete other extreme, where we actually simplified the problem to its minimum expression and substituted everything that we could not calculate by some sort of empirical approach, which of course creates a series of limitations. Now, what I'm going to try to do is bring you somewhere more towards the middle, where I incorporate more of the physics in a way such that the problem still remains tractable, but the need for these empirical formulations not only is less, but where you actually use it, it is to extract, for example, properties that are properties by themselves, so that they don't encompass a multiplicity of physical phenomena, but they're just simply a property. So, for example, finding methods to calculate an average thermal conductivity of a material that is degrading, which generally is quite a complicated thing to do. So, in essence, it's sort of trying to move away from this space of the impossible, which is the full resolution of the conservation equations that is completely intractable, because you are resolving nanoscale and nanosecond processes in a domain that basically is of the order of meters and hours. So your entire domain is too big for the time steps and the resolution that you need if you're going to resolve all those equations. Now, oversimplified solutions are too narrow in scope and too conservative, and therefore we need to find somewhere in between. And a good place to look into how to do this is material flammability. So I'm going to just simply dive into the concept of material flammability so you understand how we refine these simple models to try to obtain something that is much more that approximates much more the reality without having to go through these extraordinarily conservative systems. So this is what we did. So we took a very simple equation for the heat release rate that served as an input to the compartment fire zone models, okay? And we said it was the heat of combustion times the burning rate, megajoules per kilogram multiplied by kilograms per second gives you kilowatts or megawatts. And we recognize that the burning rate changes at a very slow rate, while the area is going to increase at a much faster rate. So we assumed this to be more or less a constant, this to be more or less a constant, and your area is the one that carries the burden of time. Okay? So the heat release rate is going to grow in time as a function of how the burning area is increasing in time. And we established the area as a function of a flame spread velocity. We input this into the equations and effectively treated all these terms as material properties. Pi is obviously a constant. The heat of combustion, we treat it as a constant. The flame spread velocity as a constant and the burning rate as a constant, and therefore lumped all this into a term called alpha. And that basically gave me the dependency of the heat release rate as a function of time. Okay? And that's what served as the input to the zone models. Now, we're going to try to look at this problem in a slightly more refined way. So the material properties, to be introduced in the design fire, that is the one that goes into the zone model, are effectively this: heat of combustion, flame spread velocity, and burning rate. Now, what we're going to do is try to use small-scale tests to gather the information about these properties to see effectively how they can be better approximated, as opposed to just simply lump them into a term called alpha. So the information that we're going to extract from this test is much easier to extrapolate so that you can actually predict the value of alpha. As opposed to just simply getting a value of alpha from a test, you're going to calculate all three components and find the value of alpha in a more refined manner. So why is this important? Because obviously many materials that we use are going to be evolving rapidly as technology evolves, and of course, as the architectural imagination takes control. So this is an interesting problem. So this is a library. It's the library of Astana. Astana is the capital of Kazakhstan, and basically they wanted to create a series of buildings that were exceptional to adorn this new capital. So they moved the capital from Almaty to Astana, and they wanted to create all these buildings, and this is one of the buildings that they created. The architect is the famous Sir Norman Foster, and he came up with this design, which is a very lightweight lattice ceiling, and then every one of these floors basically represents one level of the library. Now, these smooth surfaces here are all made out of molded or formed polyurethane, okay? Now, effectively, polyurethane can be lightweight, open-cell polyurethane that you have in this chair. Now, the polyurethane in this chair is open-cell, so that when you sit and you squeeze it, the air comes out, okay? But if you want to make it rigid, you make it closed-cell, and then you get the same material, but it's actually very stiff. Okay, and you can mold it and create these beautiful shapes. But of course, polyurethane burns. Okay, and when polyurethane burns, creates a big problem in terms of fire. So what they do is they render it with a ceramic, and that ceramic, in principle, is there to protect it. So the problem is that if you test the components all by themselves, they basically will tell you that the polyurethane is combustible. But if you test it as an ensemble, then you can argue that the ensemble, the encapsulated polyurethane, is non-combustible. So the question here is whether polyurethane encapsulated in ceramic materials can actually be used for a library. What do you think is the answer? Yeah, I mean, I think you have to be very, very careful, and this is the kind of problems that we face. So look how this material behaves when you actually expose it to heat. So the material is called Dekpol, and so we tested this. Oh, God, not again. How is it doing this? Let me see if I put it just like this. So that's the material. And basically, there's a radiant panel here that is radiating heat to the material. And very rapidly, you see that little cracks start appearing on the ceramic render. And it starts creating holes. Eventually, it exposes the polyurethane. And at some point, the polyurethane that now is gasifying because it's pyrolyzing is going to ignite, and then you get a big flame. Now, imagine the whole library cladded with this. Then you will have a very, very significant problem. So these are the kinds of things that we want to understand. Let me go back to the presentation mode. And these materials are not easy to understand. Now, look at that one. That is a mass timber material, the kind of materials that you use in timber buildings. Is basically glued layers of pine that basically can be formed in different shapes, and different sizes. They're very homogeneous in properties because, for example, in that case, it's cross-laminated timber. You put the timber like this, and the timber like this, and then like this, and by changing the orientation, you can come up with a more isotropic material. Now, you have a whole bunch of processes happening. You're going to have a drying wave. You can see the line that is drying here, and you can see it here. So it's a drying wave that basically releases the moisture of the timber, followed by the pyrolysis, followed by the char oxidation. This is a heater that is providing enough heat. So you can see the ash that gets formed in the surface. Then you get the charred part, and then the pyrolysis front, and then right around here you get the moisture front. So you can see these materials all behave in complicated ways. Now, when you arrange them in a complex way in a building, then they behave in a different way. So let's see if this works.
Oh, you may not be able
The narration is spectacular.
OMG.
He can't get out because he can't get out the door.
Oh, Jesus. They're going to bring the ladder truck over. Oh, my God.
Damn, I was going to get an apartment over there, too.
Not now.
They're cheaper now.
Yeah, pull that one.
Wow.
Pull this one up right here.
right here?
Yeah, that one.
You can feel the heat.
So the moment that you start arranging timber, leaving gaps and everything, you get radiative feedback.
This guy
you get all
is
sorts of
on
different
the
things.
freaking
And then you
ledge.
can get this
Look at this. Oh, my
extraordinary large
God.
fire.
Where?
Do they see him?
Where is it?
Oh, my Jesus. Oh, my God.
Is that a construction guy?
Yeah. He was inside there. Do they freaking see him?
They're getting them. Unbelievable.
Oh, my God.
Hurry up.
Oh,
hurry
God. Oh, God. Oh, God. Oh, God. Oh, my God. Oh, no. Oh, no. Oh, no. Oh. Oh, my God.
up. Keep going. Keep going.
Oh,
Look at the glass melting up there.
Unbelievable play.
they need to get him. Oh, Jesus. Oh, God. Oh, God.
Get closer to it.
Oh, the best part.
Oh, you may not be able.
You can jump from there. I mean, good grief.
Fucking, I'd be jumping, man.
They need to move that truck up. Oh, my God.
I don't know why they're not evacuating this.
I think that we probably should be going.
It's not time to evacuate the guys.
Just jump for it, man.
Hell yes. Oh, thank Jesus. Thank you, God. Oh, my God. Oh, no, my God. Oh.
Hey, what about this guy? What about this guy?
They got him.
Oh, okay. Oh, yeah, it's hot.
Oh, Jesus.
Oh, did you feel heat?
I think it's time for us.
So as you can see, timber can be a massive problem, and all these things need to be characterized properly, and for that, we need to this very, very simple approach, towards the fire growth doesn't apply to any of these things. So we need to try to dig deeper and try to find things that are inherent to the materials themselves, and they're not necessarily combinations of different physical parameters. Now, we said that the heat of combustion was straightforward. We can do bomb calorimetry and find those values with no problem, so I'm not going to bother with that anymore. And so in essence, I have the three things to find, and this one I already have. Okay? So I'm not going to worry about that one. So let's look at the flame spread. So how do I actually estimate the flame spread? And this is a little bit of a tricky problem, because flame spread velocities depend on a multiplicity of different things. And we need to be able to understand what are the physical parameters that govern flame spread to see what are parameters and what are physical processes. Okay? So the same thing is going to happen with the burning rate. The burning rate has a lot to do with in-depth heat transfer and the chemistry of pyrolysis of the material, and therefore is going to be subject to a number of physical and chemical processes, but at the same time there are certain parameters that I can actually extract to be able to produce a model for the burning rate. So basically this is what flame spread is. So this is the tip of the flame. So here you have your combustion reaction that is being fed by a flux of fuel coming out of the surface that is generated by the heat that is fed back from the flame. Okay? The flame is going to try to spread at a flame spread velocity, Vs, and that flame spread velocity is the result of heat transfer processes ahead of the flame. So this scenario is called opposed flame spread, because the flame is moving in this direction while the air and the fuel are moving in the opposite direction towards the flame. So if you stand on a frame of reference of the leading edge of the flame, the air and the fuel will be moving towards the flame, so in opposite direction to the spread. So the flame is going to transfer heat to the gas phase, which is going to bring the temperature from the flame temperature to the ambient temperature at a certain distance, that is delta G, which will be the thermal length in the gas phase. Now, the air has thermal properties, density, specific heat, and thermal conductivity. And in this case, I just put a forced flow, but you could actually be a buoyant flow or it could be stagnant, okay? So, but just for simplicity, I put a forced flow here, and that basically is air that has this set of properties that as it approaches the flame is going to increase its temperature until it reaches the flame temperature at the leading edge. In a similar way, the flame is away from the surface at the distance of epsilon, which is the standoff distance of the flame. And this value is always finite, because if the flame approaches too close to the surface, what ends up happening is a heat conduction into the solid, cools down the flame and quenches it. So the flame doesn't touch the solid because of heat losses, towards the surface. So energy is going to be transferred downwards through the gas phase into the solid in this direction, and it's going to heat a part of the solid. So basically, you're going to have a gradient of temperature that is going to bring you from the pyrolysis temperature at the surface down to the ambient temperature at the thermal thickness, delta T. Okay? The heat transfer in this direction is QLS, and then you have heat transfer, conductive heat transfer in this direction, which we're going to be calling QS. Now, this point is at the pyrolysis temperature, and the temperature is going to decay as you move forwards, basically back to ambient. And the solid will have its thermal properties. It's at ambient temperature at this point, the density of the solid, specific heat of the solid, and the thermal conductivity of the solid. Okay? So basically, that's the physical problem. The physical problem is a flame that is releasing energy and is transferring heat to the air to heat it up to the flame temperature, and transferring heat through the solid to bring the solid to the pyrolysis temperature. Okay? So now, how do we try to quantify this with a simple model? Effectively, what I'm going to be saying is that the flow, the mass flow of solid, density times the velocity of spread. So if you're standing on a frame of reference of the flame, the solid is coming at the flame spread velocity in this direction, multiplied by the density, you get kilograms per second per unit area. So it's per unit transversal area. So basically the section you assume is a unit area, and you are moving that mass in that direction. So the mass multiplied by the specific heat and multiplied by the increment in temperature is going to give me the total energy that I need to heat the solid. Now, the final component is the delta T. So velocity, meters per second, times delta T, which is the area, or the depth that is being heated, gives me meters squared per second multiplied by kilograms per meter cube. Now you get the actual amount of mass per unit depth. Is that okay? Okay. So effectively, you get the mass per unit depth. You assume the depth as being unity, and effectively, this is the energy necessary to bring the solid to its pyrolysis temperature. Now, you will see that here it says T ignition and not T pyrolysis, and I will explain that later. What we're going to eventually do is approximate the two to be the same. Okay? So this is the energy that I have available, and this is the energy that is being supplied per unit depth by the gas, so basically by the flame. So the flame is providing a heat flux in kilowatts per meter squared, and multiply by the preheating length, which will be this delta S, and unit depth. So you have the energy supply per unit depth. Now, there was a big debate in the 1970s about in which direction does the heat go through. There was a whole group of people led by Foreman Williams, who effectively will say that the dominant mode of heat transfer is through the gas phase. And there was a whole other group of people led by this gentleman in Spain called Sánchez Tarifa, who believed that the majority of the heat went through conduction, through the solid phase. Okay, to settle the dispute, Sánchez Tarifa, who was cousins with Amable Lignan, who was very friendly with Foreman Williams, he decided to send his nephew, Carlos Fernández Pelo, to work with Foreman Williams. And the result of that collaboration is a very, very, very famous paper called Controlling Mechanisms of Flame Spread, where, of course, as you can imagine, Foreman Williams was right, and from then on, people consider that the major form of heat transfer is from the flame through the gas phase and through the surface of the solid. Okay? Now, years later, people have been doing massive amounts of experiments, and what you end up realizing is, of course, if I increase the thermal conductivity of the material massively, in some cases, it can be through the solid. And in most cases, a combination of both. But let's assume that the heat is going in this direction through the gas phase. Most fire-related materials will have low enough thermal conductivities that generally the majority of the heat comes in through the gas phase, okay? So energy comes in through the gas phase and is delivered to the solid to bring its temperature from ambient temperature to the pyrolysis temperature or the ignition temperature, okay? And when that happens, then the flame can jump to this point and effectively has spread, and that happens at a velocity Vs. So if I just simply solve for the flame spread velocity, I have Q delta S on the top, and then rho S CPS T ignition minus T infinity times delta T on the bottom. Okay? Now I have I have to separate the problem into two, thermally thick and thermally thin. So a thermally thin material is paper, for example, where the entire section heats up. So the delta T is equal to L because the entire section is being heated up. The paper heats up entirely. Okay? So you will have delta T equals L. While in the case of thermally thick, only one, a certain part of the material heats up, so I have to estimate delta T. Now, how do I estimate delta T? I said, well, the heat that is going in is going to be transferred through conduction inside until you get to delta T, and then after that is ambient. What I do is a linear approximation for the conductive term. So instead of having the derivative dt dy, I'm going to have basically just the difference in temperature times the thermal conductivity divided by delta T, and that is going to be equal to Q gas. Then I just flip them around, and I can establish what delta T is going to be. So basically, Q gas is going to be Ks T ignition minus T infinity divided by delta T. Okay? So just a linear approximation of conduction into the solid. And I can substitute this into this equation here and calculate the flame spread velocity. Now, if you look at the model, while it's very, very simple, it does capture the physics. And it leaves you with parameters that are real. So the parameters are Cp, K, all these are things that actually are true material properties. Not the flame spread velocity as a material property, because the flame spread velocity is not a material property. Because if I change the velocity of the air, for example, I will change the value of the flame spread velocity. If I change the orientation, I would change the value of the flame spread velocity. Now, all the terms in here, to some extent, represent material properties. Now, the only problem here is that some of these parameters I cannot calculate. So the heat flux from the flame, I can probably estimate, but I cannot calculate properly. And these heating lengths, again, are actually a little bit complicated to establish, and they are not material properties either. So this is better than what I had before, but it's still not a complete picture. Now, no, obviously, depending on the materials, you will have to see if it's thermally thick or thermally thin. And I presume you've all taken some heat transfer class, so I'm not going to dwell too much on this. But effectively, we use the boundary condition to calculate a buoyant number. So basically, the thermal boundary condition at the surface, convection equals to conduction. Then I linearize the terms, and then I set up the ratio of the gradients, and what emerges on the other side is the buoyant number. And the buoyant number basically tells me whether it is thermally thin or thermally thick. Okay? In a thermally thin material, the entire material is more or less at the same temperature, so Ts minus Tb is almost 0, and the difference between Ts and the hot gases is very large, so your buoyant number tends to 0. It's much, much less than 1. Well, if you have this case, which is the thermally thick, the Ts minus Tb is very big, while Th minus Ts is very small, so you get a big number divided by a small number, your buoyant number is much greater than 1. So for fire problems, most materials are thermally thick, okay? So generally, we're going to be operating with thermally thick materials, but we can verify it using a buoyant number. So as I said, if most materials are thermally thick, I can take the equation for delta T with the linearized conduction and plug it into this term here, and I get an expression for the flame spread velocity. Now, that expression for the flame spread velocity has the thermal properties of the material, which are real properties, the ignition temperature or pyrolysis temperature of the material, which is a material property because it's the way in which the chemistry gets degraded and when I consider that I start pyrolyzing the material. Now, it is not a fundamental property, but it is a good approximation to have an ignition temperature. And then this weird oddity here, that is the combination of the heat supply times the area through which the heat comes through. And that becomes really the most complicated part of the whole problem. But here I have an expression for the flame spread velocity. Now, the way I'm going to handle it is I'm going to lump this into what I call the flame spread parameter phi. And this material property, which as a product, K rho C, is called the thermal inertia, okay? And so basically at the end, I have 3 properties that I'm going to evaluate to try to obtain an expression that describes the flame spread velocity, okay? So now, to be able to calculate the flame spread velocity, I need to first understand ignition, because I need to bring the material to ignition conditions. Now, if I just take simple timber, this is a bit of a mess, okay? And as I was explaining, there's going to be a lot of phenomena. You know, you're going to have, for example, smoldering at the surface that is going to create heat feedback. You're going to have the degradation chemistry. You're going to have heat transfer. You're going to have mass transfer of fuel coming out and oxygen diffusing in. You're going to have the water evaporation, as you can see here, which is not a very homogeneous process because, for example, in the nodes of the timber, you will get privileged migration of water. So it's a very complicated problem. So that simple expression that I've created for flame spread is one that basically already simplifies the problem enormously. So what are we assessing here? Ignition defines the onset of the fire. Ignition is going to control the flame spread because it is in the equation. But ignition is very complicated. So if I actually look at a piece of timber and I look at all the different phenomena that is occurring in a piece of timber, you're going to have, for example, as I say, diffusion of oxygen to the inside, pyrolysis gases coming out. You're going to have changes in concentration of the fuel. You're going to have changes in concentration of the oxygen. You're going to have, for example, here, radiative losses from the surface. You might be applying a heat flux from the outside. You get convective heat transfer. You're going to get a temperature gradient to the inside, and you're going to get a change of permeability of the materials you progress inside. Very close to the surface, the material is very porous, so the permeability is high, but as you get deeper in the timber, the permeability decreases up to the point where it's actually negligible. So all this phenomena is happening, and together with that, you're going to get things like cracking, for example, that are mechanical behavior, that is very difficult, to predict. So this is not an easy problem, okay? So again, we have to try to simplify it, and we're going to treat it first as a one-dimensional problem where we impose a heat flux. There are losses at the back, and I'm going to try to resolve this problem for a constant heat flux. So the energy equation is going to be conductive heat transfer, the change of enthalpy, the energy absorbed by the pyrolysis reaction in an Arrhenius form, where delta HI is each pyrolysis reaction, because you will have multiple pyrolysis reactions occurring, multiple steps, and some materials will actually absorb radiation in depth. So, for example, if you have many plastics will allow radiation to go in depth into the material, so you have to treat this as an absorption term that is occurring in every controlled volume. So you're going to have conduction, generation, in-depth radiation, and energy accumulated. Now, your boundary conditions are going to be an initial condition T equals 0, T equals Ti. At the surface, you are going to impose an external heat flux that partially is going to be absorbed if the absorptivity is alpha. You're going to have heat losses to the gas that you can approximate as convection, but let's assume it's correct term, which is conduction to the gas, because you have a non-slip condition, and basically surface re-radiation, which is radiation from the surface to the outside. And in the back, you will have some generic term of heat losses. Okay? So that's the equation that you need to solve. Again, I've already simplified a number of phenomena, haven't taken into account any of the mechanical phenomena, just simply taken into account the thermal aspects of it. Now, what I want to get is the amount of fuel that is being produced, and because that's what's going to react with the oxidizer to produce the flame, and that amount of fuel being produced, again, is the summation of all the Arrhenius expressions representing pyrolysis, multiplied by the fuel concentration, a mass fraction, because part of the fuel will actually be oxidized in depth. So this number is not going to be 1, okay? So it's going to be a number that approximates 1, but it's not going to be 1. In many times, the pyrolysis reactions come accompanied by some oxidation reactions. So what you're going to get is only a fraction of it that comes out as combustible. And then you will have some CO2, some CO coming out of the... And then accompanied by the permeability, and because depending on where you are in depth, you're going to have a different permeability, and therefore you need to solve this. Now, this permeability function, again, is very difficult to obtain, and you have to integrate through the depth of the material, okay? So basically, that's the set of equations. Now, in the gas phase, you can, with the appropriate boundary conditions, you can probably use CFD and solve what is happening at the flame level. The combustion process, can be described by the appropriate reaction rates, and ignition can be established by means of a critical concentration in the gas phase. In other words, when you reach the lean flammability limit, and that's what I described on Wednesday as a flash point. So then the flame establishes, you get the flash, and then if you have sufficient amount of fuel burning, the temperature of the flame is sufficiently high, and the flame stabilizes, and that is called the fire point, which is when you actually don't get a flash, but you get a stable flame established on top of the material, and that is more related to a critical mass transfer number, because the heat being fed back to the material has to be more than what you need to pyrolyze the material, so that you get the stable flame. So that's the process. Now, let's see how we can work this out into a solution. So as I start heating and provide this external heat, the surface is going to heat faster, and you get a gradient of temperature in depth. As time passes, the temperature gets higher, but you still have this gradient of temperature, and at some point the back starts heating up. Now, you keep increasing the temperature, and you get the third blue line. Now, if you look at the temperature as a function of time, and you have thermocouples in different positions, 1 will be the hottest, which is closest to the surface, 2 will be the next one, which is deeper, 3 will be the next one, and you keep going inwards, and that's this plot here. Now, if I take the surface temperature and just take 1, it starts at ambient and it starts growing until eventually you reach the pyrolysis temperature. At that point, when you reach the pyrolysis temperature, you start producing fuel, and if you wait for a little longer, then you reach the flammability limit, and then you can get the flash point, and if you wait a little bit longer, you get to the red one, and you can reach the fire point, and now you have a flame that establishes over the material. Okay? So if you look at the problem of just simply the thermocouple at the surface, what you're going to get is starts on ambient, starts increasing, you have time on the x-axis, starts increasing in time, until eventually starts pyrolyzing. 285 is typical for timber, for example. And then it starts pyrolyzing. You can see how it flattens because it becomes endothermic. So the pyrolysis now starts activating the chemistry, and it's endothermic pyrolysis. So it starts absorbing most of the heat until eventually you get to the flash point. Then you can see the fluctuations associated to the different flashes, and then eventually the flame establishes, and you see how the thermocouple goes up, because now you have a flame that is heating your thermocouple to a much higher temperature. Okay? So that's the process. Now, what is interesting about this is the heating process up to the point where you get to pyrolysis is inert. So because these are Arrhenius expressions, they're high activation, so at the beginning, the endothermicity is almost 0, is inert, then you get to this critical temperature, and then it takes off. And very rapidly, then it becomes endothermic. But all this period here, the heating of this solid is completely inert. So if I look at the difference between the pyrolysis temperature, the fire point and the flash point, and I say, well, these are happening very close to each other, I can forget about all the chemistry and treat the problem as an inert problem and define ignition as basically what happens up to the point where you get pyrolysis. Okay? Now, obviously, that is conservative because to get ignition, some more time is going to pass. But at least it is a process that allows me to approximate better the process of ignition. Okay? So, in essence, complete solutions are very difficult, so I need a simplified solution, and I'm going to use this concept of inert heating as the way to achieve that simplified solution. So effectively, what is what I do? Ignition delay time, so the time that it takes from exposure to ignition of a flame, which is a visible event, okay, is going to be the time that it takes to reach pyrolysis, then the time that it takes to have a flammable mixture, and the time that it takes to heat up the flammable mixture until it ignites. Okay? So the first thing I'm going to do is I'm going to ignore this TI, which is the induction time, by introducing a pilot. So the moment that I get a flammable mixture, it ignites. Now that's really good because it gives me consistency in the data, because having a pilot, I am not subject to, for example, the difficulties of heating a gas where you have a buoyant flow that can be quite complicated. So effectively, I can make this one neglectable. This has been evaluated by a number of people, and it's been shown to be less than 5% of the heating time, because the heating time until pyrolysis is the heating of a solid. So it is actually a very long period of time compared to reaching a flammable limit, which is basically the Arrhenius equation taking off. Okay, and that happens very rapidly. So basically, Tm and Ti become neglectable, and the moment you reach pyrolysis can be assumed as the ignition point. It is conservative, but it is a better approximation. Now, by assuming this, then the pyrolysis temperature then is more or less the same as the ignition temperature, and I can treat the entire solid as an inert material, okay? So the moment that I can treat the entire solid as an inert material, then what happens? The first thing is there is no more chemistry, so all the strong nonlinearity of the equation disappears, okay? Now, most materials that pertain fire are opaque, so they don't absorb in depth, they absorb at the surface. So by doing so, I can neglect that term, which effectively leaves me with conduction and enthalpy. So instead of having the properties as a function of temperature, if I actually use effective properties, I can treat them as a constant and extract them out of the equation. Now, most materials in fire are thermally thick, and therefore I can assume that the material is semi-infinite, which basically brings the boundary condition to infinity, and I can say that at infinity, T is equal to T infinity. I can linearize the boundary condition by using a total heat transfer coefficient that includes conduction and re-radiation and all the terms here. And by using global properties, I can take the K and the rho CS out of the differentials, and I get effectively a much, much simpler equation. So this is the equation to be solved, the transient heating equation, and these are the boundary conditions. Now, why am I doing this? Because I can solve this. Okay, so I can do a Laplace transformation and do a Taylor series expansion, and I can get an analytical solution for this. Okay, so this equation presented in this form has a closed form solution, and therefore allows me to basically come up with an answer for the ignition delay time. Okay, now when you look at the ignition delay time and you look at the answer, here you have the product of the thermal conductivity, the density, and the specific heat, which is the same thing that you saw on the flame spread equation. You have T ignition minus T infinity, which is the same thing that you saw on the flame spread equation, and this is the external heat flux that you are applying. Now, the ignition delay time is something that I can observe. So this is something I can measure, and I can measure it very accurately. So imagine you have a solid that you want to test. You have a radiant panel that provides a constant heat flux, okay? And you put a shield, okay? So that shield maintains this cold, okay? And then at some point, time equals 0, you remove the shield, and then you wait until a flame ignites with a pilot at the top to make your induction time negligible, okay? So I can measure the time to ignition in a very precise way. So this becomes measurable. And this becomes measurable because I'm imposing the heat flux, and I can do it for a lot of heat fluxes. So I can change the heat flux and repeat the experiment and measure this in a very simple, observable way. Okay? As a result, by knowing this too, all that I need is 2 data points to be able to solve this equation. So I put a heat flux of 20 kilowatts per meter squared, and I measure an ignition delay time of 400 seconds. Okay? Then I put 40, and I measure an ignition delay time of 200 seconds. Now, with 2 equations and 2 unknowns, I get the thermal inertia, and I get the ignition temperature, okay? Which are the 2 things that I need to plug in into my flame spread equation, okay? So the material properties end up being this, and I'm going to basically run tests to find, this, which basically allows me now to calculate the flame spread velocity, okay? So the burning rate is a little bit more complicated. Again, is the burning rate per unit volume multiplied by the volume, and you have to add the whole thing, but generally it follows a pretty complicated plot that evolves in time. The way I normally assess this is by direct measurement, and this is what we call sort of oxygen consumption calorimetry, and it is the heat release rate. So it's an indirect measurement. So how do you obtain it? Basically, you measure the heat release rate, and you do it not by putting a load cell or a scale, but by actually measuring how much oxygen gets consumed. So if I measure the mass fraction of oxygen in and out of a controlled volume, and I know what the mass flow rate is, I can actually establish the heat release rate. So this is what I'm going to be measuring, and this is a much more precise measurement than measuring the burning rate. Now, I need to find the heat of combustion per kilogram of oxygen, which effectively is a constant value. Okay? The same way that you have the heat of combustion per kilogram of fuel, if you put your equation, you can convert it into the heat of combustion per kilogram of oxygen. Okay? And that is going to give you a constant value independent of the fuel. So by doing so, I can measure the burning rate in an indirect way, which gives me the final parameter. Okay? So as you can see, these things can be obtained in a way such that are more precise than the alpha that we originally had. And so instead of having everything lumped into an alpha, now I'm going to use the material flammability properties, and I'm going to have a more precise system that actually allows me to calculate things in a correct way. Again, obviously, I'm not saying that this is a complete analysis. I'm saying it's the next level of precision. Okay? Now, a lot of the things, these material flammability properties, that you have in here, as I say, they repeat themselves in the different parameters, and so I have 1, 2, 3, and 4, and I need to be able to establish them, correctly. So basically, instead of having this very simple coarse expression, now what I have is a series of equations that have a lot more physics in it, and where the parameters that I'm calculating are actually closer to being parameters, and they're not necessarily complex physical phenomena. So what I'm going to do now is show you how it's done standardized. So these things have been standardized so that people can repeat them and verify them in an appropriate way. And I'm going to look both at ignitions of liquids and solids, and how you find these different parameters. So the simplest of them all is the liquids. I don't know if you're familiar with this. This is a Penske-Martin's closed cup test, and basically gives you the flash point temperature. Now, what it is just literally a bucket that has a little fan in there that is stirring this so that this is a constant temperature. And you provide a little bit of heat from the bottom until you reach a certain temperature. Then you turn this knob around, it opens a little window, it puts a pilot flame, and if you get a flash, that basically means you have attained the ignition temperature. Okay? And basically what that reflects is that at the opening, you are at the lean flammability limit. Now, in the case of liquids, there is no pyrolysis, so this is dominated by thermodynamic equilibrium, so it's Clausius-Clapeyron, okay? But in essence, as you increase the temperature, the equilibrium concentration increases until eventually you're going to reach the flammability limit at this point, okay? And at that moment, when you reach the flammability limit, the moment that you put the pilot, you will get a flash. And that's what's characterized as the flash point temperature. Now, what is the practical value of this? You use them for classifications. So it's pretty straightforward. Like, for example, if you have class 1A, the flash point is below 23 and the boiling point below 38. So what does that mean? That if I have a material that has a flash point that is of 23, what is going to happen when you try to store that material? Exactly. So basically, if you leave it there, it's going to evaporate, and at ambient temperature, is going to produce a flammable mixture, which effectively represents an explosion hazard. Is that okay? So from the perspective of storage, then what do you have to do with materials of the type class 1A? Sorry? Well, that's a possibility, no? So you can bring it down, so you can put them in a refrigerator and put them below, the flash point temperature. And, but the alternative is you enclose them. Yeah, so enclosures have to be completely sealed because you cannot have that. Now, as the flash point increases, and you go flash point at or above 100, these materials, for example, 3B, can be stored open, okay? Because they will never produce an explosive hazard. So people use this for storage, and basically NFPA has these ratings that basically determines what kind of storage you're going to have depending on the flash point and the boiling point. Now, why the boiling point is important? Because the lower the boiling point is, the lower the point where you're going to have a massive amount of combustible gases that come out. It's more a reflection of the magnitude of the problem. So let me look at the test. This is, again, a standardized way of dealing with this problem. So this is a standard test, the lateral ignition and flame spread test, and basically corresponds to two tests, an ignition test and a flame spread test. The ignition test is a small sample placed in front of a radiant panel that gives the sample a constant heat flux. So it corresponds to the equation I described before, okay? Now, the flame spread test is exactly the same arrangement, but now you have a long sample that goes all the way down, and the radiant heater is tilted, so you get a distribution of heat along the direction of the sample. So if you're very close to the ignition area where you have a constant heat flux, you have a very high heat flux, but as you progress away, the heat flux decays, so you're going to be measuring the flame spread velocity as the external heat flux goes down, okay? That allows you in one test to collect a number of data points for different values of the external heat flux, okay? So this is a standardized test, as I said, and basically it is the concepts I described before, but in a way that is done in a standard way. So the equation that I showed you corresponds to this type of test data. So as I increase the external heat flux, then the time or ignition delay time is going to shrink, okay? So basically, as you get to very low heat fluxes, the time to ignition or ignition delay time eventually reaches an asymptote and it goes to infinity, okay? So if I look at the data, ignition delay time, there's the asymptote, in this case, around 10. That's what we call the critical heat flux for ignition, and it's labeled Q0 ignition. And this will be the fit to the ignition equation that I generated a few minutes ago. So if I look in depth of the material, this will be the surface. All these are surface thermocouples at different values of the heat flux. As I increase the heat flux, the temperature is going to increase faster, and therefore my ignition delay time is going to be shorter. At some point, when you reach the ignition temperature, then you get ignition, and when you are below the ignition temperature, you are inert, so you're heating in an inert way. Now, as I decrease the value of the heat flux, then I still reach ignition temperature before I reach thermal equilibrium, but at every point it's getting longer and longer and longer. So my ignition delay time is getting longer and longer as the heat flux decreases. Eventually, I will get to the critical heat flux for ignition, and that's where it asymptotes, because the thermal equilibrium is attained at T ignition. And if thermal equilibrium is attained at T ignition, then your ignition delay time is going to be infinity, okay? Any value below that critical heat flux, thermal equilibrium is going to happen lower than the ignition temperature, and therefore it will not ignite. So this is your ignition delay time. If you are above the critical heat flux, your external heat flux is above the critical heat flux, then you're here and you ignite. And if you are below, then you're here and you don't ignite. Okay? So at the asymptote, the external heat flux is equal to the critical heat flux for ignition. Okay? When thermal equilibrium is attained, when the surface heats up to the ignition temperature. So again, this is the equation. These are the boundary conditions as we discussed. And in the test, you've quantified the total heat transfer coefficient. So you've measured it for the test so you know what the value is. Okay? And as the temperature goes up, the heat losses are going to increase because the surface temperature is getting hotter, so the heat losses get bigger. Heat losses are zero when the surface temperature is ambient, and heat losses reach a maximum when the temperature of the surface is the ignition temperature. So basically, as you go up towards the ignition temperature, your losses go from 0 to T ignition minus T infinity multiplied by this total heat transfer coefficient. Okay? So at this point, when you get to that point, and you are at thermal equilibrium, then the external heat flux is going to be the critical heat flux for ignition, and the losses is going to be T ignition minus T infinity times the total heat transfer coefficient. So this, when it reaches thermal equilibrium, so then from here, you can get the value of T ignition. So basically, I equate this to 0. I bring this to the other side, divide by the heat transfer coefficient, and add T infinity. And basically, T ignition is T infinity plus a characteristic temperature, which is the critical heat flux for ignition, divided by the heat transfer coefficient. Now, this term here, I'm going to measure because I start reducing the heat flux until it doesn't ignite. So I'm measuring, I know what it is. And because I know what it is, and this I have measured, I know what the ambient temperature is, so I can establish what the T ignition is. Okay? So that's the problem I'm trying to solve. This is the equation that I had developed for ignition. And as you can see, the ignition delay time is inversely proportional to the square of the external heat flux. Okay? So the ignition temperature, I already know it because I estimated the critical heat flux, and from that I got the ignition temperature. I know the ambient temperature. And I'm going to flip this around. So why am I going to flip it around? If basically I take the inverse and then the square root, so that this variable here is linear with the external heat flux. Why? Because I want to do a linear regression. Okay? So in essence, the only purpose to do this is to get statistical validity by doing a linear regression. So basically, y equals ax plus b, where in this case, y is 1 over t, square root of t ignition, x is the external heat flux, and a is all this, and b is equal to 0. Okay? So this equation forces the intercept to be 0. This becomes the slope, and basically I can do a linear regression. Now, in essence, I put all my data in this format. I do my linear regression. I force it to go through the origin, and as a function of that, I have the value already of this, and I know this, I know this, so I know this. I then plug this in here, and I can extract from the slope of the linear regression, I can extract a statistical representation of K rho C. Okay, so I know all this, and as a result, I can get K rho C. Okay, so that's the way we standardize the process, and we're going to do exactly the same thing with ignition. So you will find nowadays in most fire dynamics books, you will find these values tabulated for different types of materials. So what do I have now? I have the parameters, and I have an equation that actually provides me with the information that I need. Now, I'm not going to go through the flame spread because it's exactly the same. I'll just flip through the slides. But effectively, what you're going to do now is measure the flame spread velocity. Okay? And so you measure the flame spread velocity, the asymptote is the same, because if the material is at ignition temperature, it is already gasifying, so it will propagate at a very high velocity because it's a premixed flame. Okay? So in essence, at the critical heat flux for ignition, the two asymptotes meet, which basically allows me to confirm the asymptote. So this is what we call a flammability diagram, and basically it combines the flame spread data, which is the function of the heat flux, and you get here the flame spread velocity with the ignition delay time data, which the heat flux is here, and then this is the ignition delay time. Now, obviously, the ignition delay time requires a heat flux above the critical heat flux for ignition, but the flame spread has to be below because the external heat flux, all it does is accelerates the flame. But if you exceed the critical heat flux for ignition, you end up with a premixed flame, and you get an infinitely fast flame spread velocity. Okay? So again, what am I going to do? I'm going to take the data, and I'm going to do exactly the same thing. You know, I'm going to go through all the steps, just as I did in the previous case. You know, everything is exactly the same. But now, I'm going to make a little bit of a trick here. So to be able to link the external heat flux to the surface temperature, I need the surface to reach thermal equilibrium, okay? Which basically means that I will only ignite so that it starts spreading after a long preheating period of the sample, so that the sample is entirely in thermal equilibrium. And that's just a trick to be able to do the same type of linear regression. Because effectively, here is my flame spread equation, and I need a surface temperature, okay? So what I'm going to do is I'm going to add and subtract to this expression T infinity, okay? In such a way that I have T ignition minus T infinity. This relates to the critical heat flux for ignition, and T infinity minus Ts, you know, relates Ts minus T infinity relates to the heat losses, or, you know, to the thermal equilibrium. Okay, so Ts minus T infinity is the energy that I'm supplying at thermal equilibrium, you know, while T ignition minus T infinity is the critical heat flux for ignition. So now I can substitute critical heat flux for ignition, the external heat flux, and I can create an equation that allows me to do the linear regression that I'm looking for. Again, now the flame spread velocity is proportional to the square of phi and the square of the external heat flux. So by doing this, I obtain this. And now I flip it around again, and I get this variable is y is equal to the slope times x, okay? And that basically allows me to do a linear regression, and I can find the value of phi. Is that okay? So in essence, that's the way you standardize the tests, and now you get a table for the values of phi, okay? So the final one is the heat release rate, and as I said, basically all I'm doing is measuring oxygen consumption on the one side and oxygen mass fraction on the other side, and by doing this measurement, I can get the heat release rate. So that's an easy one, and again, I have a test that is completely standardized, and that is called the cone calorimeter, and basically allows you, you know, to find the burning rate just by measuring the heat release rate as a function of oxygen measurements that can be very precise. So a clean material like kerosene will have a very constant heat release rate, so you can apply the equation perfectly well, okay? But as you start getting more complicated materials, like gasoline, for example, that has different components, it starts distilling. So you get the first component coming out, then the next component coming out, and then you have to start having a little bit of imagination. Then you get materials like naphthalene, for example, where you have a phase change. And before, when it's a solid, it has a low heat release rate, but when it becomes a liquid, then it has a much higher heat release rate because you don't need the enthalpy of melting, okay? So, and then you can get to really complicated materials. These are the typical fire-retardant materials that many of them produce chars, and many of them have intumescent chars. So this material, for example, has nanoclays inside, and those nanoclays create a structure that effectively starts producing a very thick layer of carbon, and you're going to see the thick layer of carbon becomes enormous eventually. And these materials then start getting really, really complicated. You can see the thickness of the carbon layer that is being produced, or the char layer that is being produced on top. So these things can get very complicated. So many times people, instead of trying to resolve things at the small scale, they opt for going large. So these are two large-scale facilities, and you will find a number of this around the world. I think the biggest one still, I believe, is the FM Global one. And you can see you can put an entire storage rack. And you have here your collection, and you make your oxygen consumption measurements, and you can measure the heat release rate of this rack, okay, and obtain it directly. This is one in the UK of the Building Research Establishment. It's a lot smaller than this one, but it's still pretty big. You can actually put a one-story house in there and measure directly the heat release rate. You can indulge yourself and burn sofas and obtain the heat release rate of sofas. You know, you can do it for bunk beds, and you can do it for single beds, and whatever you want. And there is an entire libraries of these things that people have. So basically, what have I done? All I have shown you is, yes, we can go deeper. Okay, we can put more physics into the problem. You know, we can make the parameters a lot more amenable to calculation, you know, and therefore of broader use. And we can actually resolve the problem at a higher level of resolution. We can even standardize the procedures so that we can apply the appropriate statistics to this and get values that are statistically valid for this kind of things. But nevertheless, as you can see, it's just one step forwards. Okay? We have not resolved the few things, and I left a lot of things hanging in there. And when it comes to the heat release rates, what happens? Eventually you quit. Okay? And you say, well, just burn the damn thing. You know, that's all we can do, and measure whatever you can. And that's what you're going to be inputting into your model. So instead of putting my alpha T squared, like I was putting in the model, okay, you can just simply take the heat release rate data from a sofa and plug it in straight into your zone model, and you're going to get something slightly better, okay? But you will have to burn the sofa, okay? So in essence, that's kind of where we're going with the adding more and more and more physics to the problem, okay? Now, we can go further and introduce a pyrolysis model, and there's a whole bunch of people working on pyrolysis models. So instead of treating the problem as an inert heating, now you can actually introduce a pyrolysis model. You can use a TGA. You can use genetic algorithms, for example, to extract from TGA data your kinetic parameters, and then you use it as input into the equation that now is not anymore an inert solid. And you can take that step. You know, you can go to Nancy in France and talk to Pascal Boulet, and Pascal Boulet will make all the optical measurements that show you what the absorptivity, the in-depth radiation, everything of different materials are. And now the term doesn't have to have, you know, a neglectable or an opaque assumption where you neglect in-depth radiation. And we can keep going and going and going and going and going to higher and higher level of complexity. But what ends up happening is that you're beginning again to approach the level of intractable. And you always have to ask yourself the question, is it worth it? Okay? So basically, I've walked you through part of the path. Now, let's take a break. And what I'm going to do next is just wrap up with the second part of the problem, which is the fully developed compartment. And I'm going to use the very simple theory for that one. And at the end, I'll show you how it can get a bit more complicated. And the final hour, I will address some of the things that you asked me and give you a perspective of what the future of fire safety looks like. Okay? So let's take 10 minutes or so, and then we can get started again.